Welcome to the deep dive. Today, we're tackling a massive challenge, a high-speed, high-density knowledge refresh for the CompTIA Cloud Plus exam, the CV0-004.
And this is a big one. It's not just about passing a test. It's about really proving you have deep expertise in cloud engineering. We're talking advanced architecture, automation, security, the works.
That's right. And the CV0-004 exam is very scenario-heavy. I was looking at the breakdown, and cloud architecture is what, 23%?
A huge chunk. That and cloud security, which is another 19%. So you absolutely cannot just memorize definitions. You have to understand the implications of choosing, say, one service model over another.
So our goal today is to synthesize all steps of those major domains, from architecture and deployment all the way to DevOps and troubleshooting. We want to pull out those critical scenario-based nuggets you're going to need.
Think of it as a mental prep for those really specific questions, the ones that need you to connect the dots, not just recite a fact.
And because mastering this much interconnected information, it really requires some precision in how you study.
It really does. Especially when you're drilling down on those complex terms. We've seen a lot of success with tools like Flash Genius. They're built for this kind of thing.
How so?
Well, they specialize in turning these dense, scenario-based concepts into knowledge you can actually access under pressure. They often use spaced repetition to make sure you really retain those tricky comparisons.
Like the difference between an NLB and an ALB.
Exactly that. Those things that you just have to know cold. So, yeah, efficiency is everything when the scope is this big.
I agree. So let's start where the exam starts. The architectural foundation, the biggest single domain.
Let's do it.
Okay, unpacking architecture. We have to start with the service models. These really dictate everything, don't they? The control, the responsibility.
Absolutely. So you start at the bottom with the nails, infrastructure as a service.
Maximum control.
Maximum control. You get the OS, the middleware, the applications. It's all yours. So if you have a legacy app that needs a very specific setup, IaaS is probably your go-to.
But with that control comes the most work, right? The highest overhead.
Exactly. You're on the hook for patching that OS, maintaining it, everything.
And as we move up that stack.
Then you hit PaaS, platform as a service. Here, the cloud service provider, the CSP, they handle the underlying OS and the runtime.
So you just focus on your code.
Your code and your data. It's a huge reduction in maintenance overhead. Think managed databases, app development frameworks, and then at the very top, you've got SaaS.
Software as a service. The most abstracted.
Totally. The vendor manages literally everything. Your email service, your CRM, you just use it.
Now, in the CV0-004, it specifically calls out some of the more modern architectural styles, like microservices. That brings us to FACE, right?
It does. FACES, or function as a service, it's absolutely crucial for event-driven, truly serverless architectures.
So you're not even managing an application server.
Not at all. You're just uploading small code functions that run in response to a trigger, a file upload, a database write, an API call. That's it.
Yeah.
It's the ultimate trade-off of control for minimal operational overhead.
And no matter which of these models we pick, the security conversation always comes back to one thing.
The shared responsibility model.
Yeah.
And you have to know this boundary precisely for the exam. The customer always owns the security of their data, their access management, their client-side encryption, always.
And the CSP is responsible for security of the cloud.
Right. The physical data centers, the hardware, the core networking, the middle ground, things like OS security, network controls, that's what shifts. In IaaS, it's mostly on you. In PaaS, HaaS, or SaaS, it's mostly on the CSP.
Okay, that makes sense. Moving on from how we deploy to how we keep things running, resilience. We have to talk about high availability and DR, driven by those two key metrics, RTO and RPO.
RTO, recovery time objective. That's all about speed. It's the maximum amount of time your application can be down.
How fast do you need to be back online?
Exactly. And RPO, recovery point objective, is about data. It's the maximum amount of data you can afford to lose. These two numbers drive every single DR decision you make.
So if I have an RTO of, say, 15 minutes, that means I need to be back up really fast. That immediately rules out the cheap options, doesn't it?
Immediately.
Yeah.
An aggressive RTO forces you into the more expensive solutions. And that brings us to the three main types of DR sites. A hot site is basically a mirror of your production environment.
Fully operational, ready to go.
Ready to fail over in minutes. It gives you the lowest possible RTO and RPO, but it's the most expensive because you're paying for two of everything.
Okay, and the middle ground.
That's your warm site. It's partially configured. You've got the hardware, maybe some basic software, but you have to do some manual work to bring it online. Restore data from backups, startup services.
So the RTO is longer, Maybe a few hours.
Several hours, typically.
Yeah.
It's a balance of cost and speed.
Hmm.
And then there's the cold site.
Just a building with power and cooling.
Pretty much just the basic infrastructure you'd have to bring in and configure all your own hardware and software. The RTO could be days, but the ongoing cost is minimal. It's only for services that can tolerate being down for a long time.
That talk about cost leads us right into data storage and tiering. How do we match the data to the cost?
Because not all data is created equal,
Yeah.
right? We optimize with 4 main tiers: hot, warm, cold, and archive.
Hot storage is for the stuff you need right now.
Constantly. It's provisioned on high-performance storage, like SSDs. You'll even see it called hot SSD by some providers. This is for your transactional databases, your OS disks, anything needing high IOPS and low latency.
Then you move down the frequency curve.
Right. Warm storage is for less frequently accessed data. Think monthly reports. It's a balance of performance and cost. Then you get to cold storage.
For things you rarely touch. Historical data, maybe?
Exactly. Audit logs, compliance data. Retrieval isn't instant, but it's not super slow either.
And for that long term, I have to keep this for 7 years, but I'll probably never look at it. Data.
That's archive storage. It's the absolute most cost-effective option for long-term retention. Retrieval can take hours, but the cost per gigabyte is incredibly low. Perfect for compliance data you just have to hang on to.
So we've tiered the data for cost, but we also have to decide how to access it. That brings us to block, object, and file storage.
Right, the 3 main types. Block storage is all about performance. It's like a raw, unformatted hard drive for your VM.
Lowest latency, highest IOPS.
The best choice for VM disks, databases, anything transactional. It's like a local disk.
Okay. And object storage.
Totally different. It's for massive scale and durability. For unstructured data, you access it via APIs over HTTP. Think backups, data lakes, static website assets. It's way cheaper for bulk data, but the latency is higher than block.
And finally, file storage.
File storage is for your traditional shared file systems, using protocols like NFS or SMB. You need this for legacy apps that expect a shared directory structure, or when lots of users need to access the same files at once.
All right, let's navigate the cloud itself, the network. The VPC is our foundation.
The virtual private cloud. It's your own logically isolated slice of the public cloud. And inside that VPC, you define your network with subnets, route tables, VLANs, all the familiar concepts.
And connecting that VPC back to our own data center, we have a critical choice. VPN or a dedicated connection.
A VPN is a secure, encrypted tunnel over the public internet.
Yeah.
It's flexible, it's cost-effective, but the performance can be inconsistent. It's riding on the public internet, after all.
Versus a dedicated connection.
A dedicated connection is a private, physical fiber link straight from you to the CSP. It's way more expensive, takes longer to set up, but you get guaranteed, consistent, low-latency performance.
Well, what happens when things get more complex, like connecting multiple VPCs, a dev VPC, a prod VPC, a shared services VPC?
For a simple setup, you might use VPC peering. That's a direct one-to-one link between 2 VPCs. Works fine for 2.
But not for 10.
Out of 10, you'd end up with this crazy spaghetti network of peering connections that's impossible to manage.
Which is where the modern solution comes in.
The transit gateway. It's a game changer. It acts like a central hub, a cloud router. You connect all your VPCs and even your on-prem network to this one central point.
It simplifies everything.
Dramatically. It centralizes your routing, your security, your monitoring. It's the way to go for complex networks.
Okay, let's hit load balancers. This is a huge architectural decision, and the exam really tests the difference between layer 4 and layer 7.
It's all about where the intelligence is. The network load balancer, or NLB, operates at layer 4, TCP, and UDP.
Oh, that's speed.
Pure speed. High throughput, ultra-low latency. It just looks at the IP and port and forwards the traffic. It's a workhorse. You use it for things like database clusters or gaming servers where raw performance is everything.
So NLB for speed. What about the ALB, the application load balancer?
The ALB is smarter. It's layer 7, so it understands HTTP and HTTPS. It can look inside the request.
At the URL, the headers.
Exactly. So it can make intelligent routing decisions. It can send traffic for checkout to your payment servers and traffic for images to your static content servers. It's what enables microservices architectures.
And the application gateway.
You can think of the application gateway as a sort of supercharged ALB. It adds extra layer 7 features, like a built-in web application firewall, WF, and it can handle SSL termination for you.
But the fundamental choice is L4 versus L7.
Speed versus intelligence, that's the core decision.
Before we leave architecture, let's touch on high-performance computing, HPC. It has very specific needs.
Extremely low latency, massive throughput for things like complex simulations. The single most critical factor for HPC in the cloud is node placement.
You mean making sure the computers are physically close to each other?
Physically very close, in the same rack, on the same network switch if possible. Many CSPs offer placement groups or affinity groups to guarantee that low latency proximity. You need that for the nodes to communicate fast enough.
Got it. And finally, the CV0-004 touches on emerging tech. What do we need to know about AI, ML, and IoT?
You need to know the practical applications. Things like automated text recognition for pulling data out of documents or visual recognition for identifying objects and images.
And sentiment analysis. What's the use case there?
Imagine you have a flood of customer reviews. Sentiment analysis can automatically read all that text and figure out the tone. Is it positive, negative, neutral? It's huge for gauging market reaction in real time.
And just a basic awareness of generative AI and IoT.
Right. Understand the basic IoT architecture sensors, gateways, and how they send data to the cloud.
Wow, that was a serious sprint through architecture. It really highlights why you need efficient, scenario-driven study tools.
Absolutely. If you're mixing up a transit gateway and VPC peering, drilling those concepts with a tool like Flash Genius is exactly how you solidify that knowledge for the exam.
All right, let's shift gears into our second domain, deployment and migration, getting things into the cloud.
Let's start with the deployment models, the basics. You've got public cloud, which is the shared multi-tenant model. Private cloud, which is dedicated infrastructure for one organization.
On-prem or hosted.
Right. Then hybrid, which is a mix of the two. And community cloud, which is shared infrastructure for a group of organizations with a common interest, like government agencies.
And the migration types cover the direction of travel.
The most common is obviously on-premises to cloud. But you also have cloud to cloud, moving from one provider to another.
Maybe for a better feature or a better price.
Exactly. And, crucially, the exam acknowledges cloud to on-premises, a reverse migration.
Why would you do that?
Sometimes you find that a workload has latency needs that just can't be met in the cloud. Or maybe a predictable massive workload turns out to be cheaper to run on hardware you own. It happens.
Okay, so the core of this domain is really the 6 Rs, the strategies for migrating the applications themselves.
It is. And it's all about the trade-off between effort and benefit. The simplest path is rehost, or lift and shift.
You just move the application as is.
Exactly. Straight into a cloud VM. It's fast, it's cheap up front, it's great for simple web apps, or if your data center lease is about to expire, but you're not getting any cloud-native benefits.
So it's a quick win, but maybe not the best long-term solution.
Correct. The next step up is re-platform, or lift and tinker. You move the app, but you make a couple of small changes to take advantage of the cloud.
Like what?
A common one is moving from a self-managed database on a VM to a managed database service from the CSP. The app code doesn't change much, but the platform underneath gets a lot better.
And if we want to go all in on cloud features?
Then you're looking at re-architect or refactor. This is where you significantly change the application code itself, breaking a monolith into microservices, for example. It's the most work, but it gives you the biggest long-term payoff in scalability and cost.
And the last two are retain and retire.
Right, just keeping things on-prem or decommissioning them.
Okay, so once the app is in the cloud, we're constantly updating it. We need deployment strategies that don't break things.
We have to minimize the blast radius of a bad deployment. The most basic is a rolling deployment.
You update one server at a time.
Sequentially, yeah. It's low cost and you don't have a full outage, but it's slow. And for a while, your users might be hitting a mix of the old and new versions.
How do we get zero downtime and a quick rollback?
That's the blue-green strategy. You have two identical production environments. Blue is live, green is the new version.
You test green and then just flip the switch.
You flip the switch, traffic instantly moves from blue to green. And you keep blue running for a bit just in case you need to flip back. The downside is it's expensive. You're running double the infrastructure.
And what if we want to test with real users before we commit?
That's a canary deployment. You release the new version to a tiny subset of users, 5%. You watch them closely, monitor the metrics. If everything looks good, you gradually roll it out to everyone else. It's the best way to mitigate risk.
And the last one is in place, which sounds risky.
It is. You just upgrade the existing application directly.
Right.
It's simple, but it has the highest risk of failure. Not for critical systems.
All of these strategies are really enabled by CI/CD pipelines. What's the key benefit the exam wants us to know?
The core benefit is faster, more reliable delivery, period. By automating the build, test, and deploy process, you get rid of human error. It means you can push out frequent updates quickly without sacrificing quality.
Okay, that takes us to our next major domain, operations and observability, keeping the lights on.
And in the modern cloud, this is about more than just monitoring. It's about observability.
What's the difference? Why is that distinction so important now?
Well, traditional monitoring is about asking questions you already know. Is the CPU high? Is the disk full? Observability is about being able to ask new questions to understand the internal state of your system, especially when something unexpected happens.
Which is vital in a complex microservices world.
Absolutely. And it's built on 3 pillars: logs, metrics, and traces. Each gives you a different piece of the puzzle.
Let's start with logs, the forensic narrative.
Logs are your detailed, time-stamped records of events. They are absolutely essential for root cause analysis after something goes wrong. And operationally, you have to have a solid plan for collection, aggregation, and retention.
You mentioned the ELK stack as a common toolset. What's the specific role of Logstash in that?
Logstash is the processing engine. It takes in raw logs from all over and cleans them up. A key function it performs, and one that comes up, is its ability to flatten deeply nested JSON logs.
Making them easier for a human to read.
Exactly. It turns that complex hierarchical data into a simple, readable format for analysis.
Okay, next up, metrics. The numerical pulse.
Metrics are your numbers: CPU usage, error rates, queue depth. They're what you use to track the overall health of the system over time, spot trends, and critically trigger alerts.
So metrics tell you that something is wrong.
They do, often before you even know what is wrong.
And that's where traces come in, to connect the dots.
Precisely. A trace follows a single user request as it travels through your entire distributed system. It shows you the whole journey, from service to service, database to database, and how much time was spent at each step.
So if there's a slowdown, the trace shows you exactly where the bottleneck is.
It's the only way to diagnose latency in a complex microservices architecture. So altogether, metrics tell you something's wrong, logs tell you why, and traces tell you where.
That observability often triggers automation. Let's talk scaling. Horizontal versus vertical.
Horizontal scaling means adding more machines, more nodes, going from 2 web servers to 3. It's the preferred cloud method because it builds in resilience.
And vertical scaling.
That's making your existing machine bigger. More CPU, more RAM. It's simpler in some ways, but it has an upper limit, and it often requires downtime to resize the instance.
So let's take a classic e-commerce scenario.
Yeah.
A big holiday sale is coming, and you expect 10 times the normal traffic. How do you handle that cost effectively?
The only sane way is with automated horizontal autoscaling. You set a minimum and a maximum number of servers. As the load increases, the system automatically adds new instances to handle the surge.
And then it removes them when the sale is over.
Exactly. It scales down automatically, so you're not paying for all that extra capacity for the rest of the year. It's the definition of cloud elasticity and cost effectiveness.
Let's talk backup and recovery. If an executive tells you, I need a guarantee of no data loss, what's the one thing you have to test for?
You have to test for integrity. It's not enough to know the backup exists. You have to verify that the data within it is uncorrupted and can be restored to its original state. That means performing actual test restores.
And what if that backup data has to cross an untrusted network to get to its destination?
Then encryption becomes the single most important feature. Encryption in transit, encryption at rest. If that data is intercepted on a public network, encryption is the only thing that ensures its confidentiality.
And for recovery, especially from something like ransomware, what's a common method?
Volume snapshots are fantastic for this. They are near instantaneous copies of a data volume. They allow you to roll back to a known good state in minutes, which drastically reduces your RTO.
To wrap up operations, let's talk about the resource lifecycle, specifically change control. What's the most important part of any plan to deploy an update?
Having a rock-solid rollback plan. Before you push any change, you have to know exactly how to undo it if things go wrong. If a patch breaks an application, you need a documented, tested procedure to revert to the previous stable state immediately. It prevents a minor issue from becoming a major outage.
Moving into our next big domain, security and governance. This is another 19%er, so it's critical. Let's start with the vulnerability management cycle.
It's a continuous process. You start by defining your scanning scope. Then comes identification.
Finding the vulnerabilities.
Right. Using scanning tools, checking against databases of known flaws like the CVE list, After you find them, you move to assessment and prioritization.
Figuring out which ones are the most dangerous.
Exactly. And then the final most important step is remediation. That's the action phase. You're applying patches, closing ports, disabling weak TLS ciphers. You're actually fixing the problem.
The exam loves to give you scenarios where you have to spot the attack vector. Here's one. A startup has a database breach right after pushing code to a public GitHub repo. What's the most likely cause?
Oh, that's an easy one. Hard-coded credentials. Someone left a database password or an API key right there in the source code. It's one of the most common and most devastating mistakes.
Okay, scenario 2. A vulnerability scan flags an open port 21 TCP. What's the issue?
Port 21 is FTP, File Transfer Protocol. That flag means you're using an insecure protocol. FTP sends everything, including usernames and passwords, in clear text, unencrypted.
A huge data leak risk.
A massive one. The fix is to disable FTP and enforce secure alternatives like SFTP or FTPS.
How about a more subtle one? Logs show some weird activity on a high port, like 8048, and the connection state is time wait, right after a huge amount of data leaves your network.
That screams data exfiltration. The time wait state on a non-standard port after a big outbound transfer suggests a compromised machine was used to shovel data out to an attacker's server. They use those weird ports to try and bypass firewall rules.
Let's touch on one more log indicator. You see a process running with a user ID of 0 as the root user, and it's executing a strange command.
Text-hook privilege escalation. An attacker has found a way to gain the highest level of access on that machine. UID 0 is root. That instance needs to be isolated for forensic analysis immediately.
All right, let's talk IAM, Identity and Access Management. Here's a process question. You're onboarding a new team member who's going to handle sensitive data. What is the absolute first thing you must do? Before training, before giving them access?
You must verify their security clearance or authorization level. Access to sensitive data is governed by strict policy. You have to confirm they are authorized to even handle that class of data before you do anything else.
Can you quickly break down authentication, authorization, and accounting for us?
Sure. Authentication is proving who you are. That's your password, your MFA token. Authorization is what you're allowed to do once you're authenticated. That's typically handled by role-based access control, or RBAC.
Your role defines your permissions.
Exactly. An auditor has read only, an admin has full control. And accounting is the log of what you did. It's the audit trail, critical for compliance and security monitoring.
And speaking of compliance, what are the key industry standards we need to know for the exam?
You need to know the big three. SOC 2, which is about security, availability, confidentiality controls. PCI DSS, which is mandatory for anyone handling credit card data. And ISO 27001, the International Standard for Information Security Management.
Let's put governance into practice. An engineer writes a helpful script to automatically increase small storage volumes. It seems like a good idea. What must they do before running it?
They must seek formal approval before continuing. It doesn't matter how small or beneficial the change seems. Bypassing the official change management process is a major governance violation. You have to prevent shadow IT. And this ties into contracts, too. Yeah. If you're working with a vendor and the project scope is very clear and stable, you should push for a fixed-price contract. It shifts the financial risk to them.
Okay, next domain. DevOps, fundamentals, and infrastructure as code. It's only 10%, but it's the glue that holds modern cloud ops together.
It really is. It starts with source control, usually Git. You have your code commit to save changes locally, a code push to send them to the remote repo, and good branch management to keep work isolated.
And how do we get that work back into the main code base safely?
That's the pull request, or PR. It's the formal process for submitting your changes for review. It's a quality gate. It triggers code reviews, automated tests, and approvals before anything gets merged.
Let's talk about the as code part. Infrastructure as code and configuration as code.
This means defining everything. Your servers, networks, firewalls, software installations in declarative configuration files, usually YAML or JSON.
So your infrastructure is version controlled, just like your application.
Exactly. And that leads to two incredibly important concepts: repeatability and drift detection.
Repeatability is just being able to build the same environment over and over again, right?
The exact same environment, every single time. It's critical for creating identical dev, test, and production environments. And drift detection is how you make sure it stays that way. It's the process of scanning your live infrastructure to find any changes that were made manually outside of your code.
Someone SSH'd in and changed a setting.
And that's drift. It breaks the integrity of your as-code model. Modern tools can detect and even automatically remediate that drift.
Can you just briefly name the key DevOps tools the exam covers?
Sure, for IAC, especially in the multi-cloud world, it's Terraform. For configuration management, ensuring servers are in a desired state, it's Ansible. And for containerization and orchestration, it's Docker and Kubernetes.
Perfect. On to our final domain, troubleshooting. This is almost always presented in scenarios.
The mindset is key. First, identify the problem. Second, theorize the cause. Third, test your theory. And when you're reporting success back to leadership, you use key performance indicators or KPIs to prove you've met your goals.
And for giving stakeholders a quick live view.
That's a dashboard, a visual, real-time summary of your key metrics.
Let's run through some specific network troubleshooting scenarios. First, an easy one to miss. You need 8 VMs for a training class. The tech uses a 29 subnet. Why can't everyone connect?
Classic subnet exhaustion. A 29 network gives you 8 total IP addresses, but you lose 2. One for the network address and one for the broadcast address. That leaves only 6 usable IPs for your 8 VMs. 2 people are out of luck. It's a fundamental subnetting mistake.
Ouch. Okay, scenario 2. A site-to-site VPN tunnel shows it's established and working. External users can connect just fine, but internal users at the main office can't reach the cloud resources. Where do you look?
The tunnel is up, so the problem isn't the VPN gateway itself. The issue is routing. The cloud network doesn't know how to send the return traffic back to the office's internal network. You need to review the development network routing table in the cloud and add a route that points the office's IP range back through the VPN gateway.
Last network 1. A latency-sensitive trading application is slow. CPU and memory are fine, but the network out metric is way higher than network in. What's the problem?
The application is trying to send out way more data than the instance's network card can handle. It's a network throughput bottleneck. The fix is to move the application to a network-optimized instance type that has more bandwidth.
All right, a couple of security troubleshooting scenarios. How do you spot a DDoS attack in your logs?
You'll see a sudden, massive spike in access requests, usually from all over the world. That will be followed almost immediately by a wave of server errors, typically 502 bad gateway errors, as your front-end systems get overwhelmed and can't reach the back end.
Last one. This is about risk versus issue. A known risk, say, a software dependency is nearing its end of life, hits its trigger. The EOL date is 30 days away. The failure hasn't happened yet, but the trigger has been pulled. What do?
You don't wait. The risk trigger has been met. The immediate action is to execute the contingency plan. That plan was created ahead of time for this exact situation. It might be to start migrating to a new dependency or deploy a workaround. You act proactively before it becomes an actual issue.
And that is a full run-through. We've navigated a really dense, deep dive across all 6 domains of the CompTIA Cloud, plus CV0-004.
And it really shows this exam demands a holistic understanding. You need to know the architecture, NLB versus ALB, tiered storage, but also the operational side, like observability and change control.
It's all about connecting those dots, knowing that security clearance comes before system access, or that a 29 subnet won't work for 8 VMs. It's that practical, scenario-based knowledge.
Absolutely. Success here is not about memorization.
So for all of you in that final stretch of prep, remember that practice and repetition are what turn this knowledge into a skill you can use on exam day. And integrating tools like Flash Genius is specifically designed to help you drill these interconnected concepts and build that confidence.
And as we wrap up, here's a final thought to chew on. If modern cloud systems are so complex that traditional monitoring is no longer enough, and we need full observability, how much of a cloud engineer's future job will be about automating the measurement of systems, not just their deployment?
A great question to think about as you get ready for your exam and your next project. Thank you for joining us for this deep dive into the world of cloud architecture and operations. We'll see you